Great. Good afternoon, everyone. And yeah, thanks for coming out here. I realized I changed the title of my slide last minute and forgot to include the word hallucinations, which could have maybe attracted more people. But I promise the next 30 minutes will be very interesting. So my name is Atin Sanyal. I'm one of the founders of a GenAI evaluations company. It's called Galileo. And we're about 3.5 years old as a company, and over time we have had the privilege of working with many leading enterprises in helping them productionize very critical LLM applications, especially over the last about year or so. Just a little bit about me. I've spent most of my career building ML infrastructure and ML systems, mostly at larger companies. The highlight of my career was about half a decade I spent at Uber in their early days of machine learning. And I was part of a team known as Michelangelo, which built Uber's end-to-end AI platform. So a lot of lessons there around key issues in ML workflows which lead to these models not performing very well. And we started the company in February of 2021. So that's about 3.5 years in. And we started off as a language modeling company because we ended up in a lab at Stanford, and it was a language modeling lab. And the whole thesis of the company was around the fact that evaluation tooling for machine learning was broken. And I had seen for 10 years how difficult it was to say yay or nay on how good or bad a model is. And people used very myopic approaches, which led to tons of issues when you productionize the model. And we started off saying that unstructured data is a sleeping giant. This was back 3 years ago, which it's interesting how we would organize webinars about unstructured data and deep learning, and I would have all the pizzas and all the burgers and all the beers, and 0 people would show up. And we recently did a webinar where about 15,000 people showed up. So it really shows the elevation in interest in this area. In fact, for 2 years, we built a beautiful tool that allowed you to improve your natural language models while you're training them. This is a screenshot of the tool where you would get this X-ray view of the data using the embeddings, and you can see areas and regions, the reds in those clusters where the model would perform poorly. And the whole thesis was that it's really all about the data. Of course, the last year, we've spent a lot of time building very similar evaluation tooling for generative models. So this is a bit of the timeline around certain achievements we've had as a company. We started in 2021, and sort of a year in, we created the first metric for evaluating language models while you're training them. It was called DEP, or data error potential. And essentially, we built a hook which would go into while the model was training, it would go into the depths of the neural net, and we would observe the convergence of the logits to the labels, and we would find anomalies in them. And then maybe about a year later, we created a semantic drift detection algorithm, which worked at much higher accuracy than traditional sort of hierarchical based algorithms that would detect semantic drift. And then 2023 onwards, of course, the whole world changed. Everyone pivoted to LLMs, and we've done tons of research on particularly hallucination detection. We created a method called chain poll, which I'll talk about today, around how you can combine chain of thought prompting with ensembling to achieve high accuracy hallucination detection methods. Chain poll was great. It relied on the power of LLMs. It was essentially a framework where you could plug and play LLMs. But it essentially relied on you using a third-party API call, which in 2024, as enterprises that you saw on the list have started productionizing, we realized that evaluation has become a multi-million-dollar problem because you cannot make so many LLM calls at scale, which was primarily most of the techniques around hallucination detection, which were published in 2023, essentially were around some form of making multiple calls to LLMs and doing checks around how much difference is there in the output. So we innovated and sort of re-thought about the problem of hallucinations, mainly for RAG systems, or RAG, retrieval augmented generation, for those who don't know, which has become the most standard paradigm at least now in enterprise, and that also is evolving into very interesting patterns. But defining hallucination for RAG, redefining it rather, we were able to achieve methods that would use much smaller models, which I will also speak about today, in detecting hallucinations, which beat Chain-Pole's benchmark accuracy. And finally, I think I'm going to start off the presentation with another observation that we've made as we've worked with these enterprises in productionizing their application, which is the need for what we call real-time interception. And I added that in the heading of the slide. And that's essentially, let me maybe get into that. So here, we see like evaluation of GenAI systems and LLM systems as a three-pronged problem. The first is, of course, while you're building your application, it's if you look at the stack that you're using to build your application, there's the infrastructure, you have vector stores, databases sitting on top of that, and then there's orchestration systems and tools like LangChain, Llama Index, AutoGen, etc., which people are using to stitch together these LLM systems. And while the stack is fairly better than making bespoke calls to LLM APIs, they help you curate more sophisticated applications. They give you tools and agents out of the box. So that's great. But there's a whole slew of challenges when you're building something using these frameworks. You can get to a quick, weak prototype pretty quickly, but there's a lot of questions that people have around what's my best prompt? Or how do I get to my most ideal prompt that would give me most bang for the buck? If I'm using vector stores and RAG, of course, for every request, I'm picking up certain data from the vector store, indexing it, and getting the raw data in. There's challenges around context length, because if you're making an API call, tokens means money. Not just that, of course, the quality of the output is also very important. There's a paper in 2023 by DeepMind called Lost in the Middle, which talks about how big the context should really be. If you supply too much data, the LLM performance really goes down. So when you're evaluating your application during development, these are the questions that you're trying to solve, trying to get to the ideal set of parameters. And then once you productionize your application, you want to monitor things like hallucinations, things like PII detection, and which my previous presenter spoke about. Those are very common problems in the enterprise, but you want to do them in real time. But the more important thing that we've realized now is that observability is one thing. It's good, but it's reactive. You might, you see an anomaly, or you might detect a hallucination, and you get a pager duty. That's great, but by the time the damage is already done, and the reason for that is in modern times, the output of these models, these systems, have basically become the product, which was not true with machine learning for most part in yesteryears. You might have a recommendation system model that would give you a ranking, and if the ranking's a bit off, that's fine. You see some off restaurant recommendation on Uber Eats, not a big deal. But here, if you're building a chatbot system and the LLM says something wrong, that's where you need real-time interception. So which is why we've built these three products. Like in our platform, there's a suite of 3 products that we offer. So the rise of real-time interception. Now, of course, I talked about this being a 3-pronged problem. There's experimentation, evaluation, and which is proactive. You're building a system to make it more robust, make sure that it works for your use cases. Then there's observability, which is also needed, but it's reactive. Interception gets into interactive mode, where not only are you trying to detect a hallucination, but you're trying to redact a hallucination. You're trying to steer your responses, well, first evaluate and gauge them, and steer them to safety if it's not meeting a certain standard. And then how do you build a programmatic framework which lets you do stuff like this, including things like auto-retrying. Say if the quality of an agent output is not good, you want to retry and so how do you automate all of this? This is what, in crux, what interception really is. Just to dive a little bit deeper, this is the boxes that you see. It's a 10,000-foot view of your entire LLM system. You have the query, the model response, and finally the application response. But there's a lot that can go wrong in the middle, and this is just touching the surface for simplicity's sake. But on the input side, for example, there's prompt injections, which is a common paradigm, jailbreaks, suboptimal input query, which is the most common problem, especially if you're sort of just building in the dark. Your single prompt and your single query will not work for all your use cases. PII leakage is a very big problem we've seen in the enterprise that users want to solve for. And then on the output side, there's hallucinations. There's embarrassing mistakes, often the output of people being able to trick the system by supplying some kind of tricky input. There's data leakage in many forms. There's incorrect outputs, there's harmful content, and the like. So what we've done is we've kind of created this purple box below this system, which allows you to author rules and employ them at different parts of your ML workflow. So the way it kind of comes into play is something like this, where the image that you see on the right-hand side of the image, you have the chatbot. You kind of go through the protect system. It would evaluate your inputs, go to the LLM, get the output, evaluate your outputs, and then apply a sort of a rules engine to be able to, almost like a gateway, to be able to do select the appropriate response based on a set of rules. So how protect works, I'm going to breeze past this because I realize I have 8 minutes and I want to get to the crux of the hallucination detection bit. Super simple. Here you have a node users building their sort of LLM systems in their notebooks. Simultaneously, there's application code. What we've done is we've added a rule set authoring mechanism, which allows you to create rules that you want for your chatbot system or any kind of LLM system, which you register to a centralized store. And you can start using and reusing these rules across your organization. And we give you a nice control panel, almost like if you've worked on configuration systems like change listening configs, which allow you to tune certain knobs to make your system operate a certain way. It's very similar, except this is for the inputs and outputs of the LLM. This is getting into the code of the same thing. It's fairly easy for the developers. It's very it's almost very modular to author rules and sort of employ them into your system. This is how the mission control kind of comes across. You get alerts if certain rules are triggered, and you can monitor all of this and go deep into the chain and root cause, where a rule may have broken. Anyway, now one of the challenges that has, of course, emerged is there's a need for LLM evaluation methods, particularly hallucination detection methods that need to be accurate. They need to scale, which means they need to work across a diverse range of tasks. They need to be cost effective, which has been a more recent challenge, and I'll talk about that. And then finally, these are all real-time systems, so there's a need to solve it at low latency. So a lot of challenges here, and here's how we have taken like a sort of a two-pronged approach to hallucination, resolving hallucinations. And this is about a 2-year story for us, because we've literally been very deep into understanding and solving for state-of-the-art modern-day LLM hallucinations. So the first technique that we built, this is probably fall of 2023, we published a paper. If you just Google chain poll, you'll find the paper on arXiv. You can read it. It's essentially introducing the first framework that uses chain of thought prompts and ensembling, I'll talk about that, to detect hallucinations. Now, chaining, what we do is, the first phase of chain poll is chaining, where we create a chain of thought prompt. And that's really the secret sauce. We worked for a long time on really curating a chain of thought prompt, which essentially gets the LLM to think step by step about its response to make itself realize where it may have made a mistake. And then we combine that with polling or ensembling, which is, if you've built random forest models before, it relies on this power of multiple decision trees, and you do ensembling. It's kind of based on the same principle, where you're it's a boosting mechanism where you do number of reruns on the LLM, and then you assert how much difference is there in the output. So here's how it works. You have a user, it supplies a query to the LLM, you get a completion, and in many cases you get what are called log probabilities. The reason we need log probabilities is to measure what we call entropy. And without getting into details about what kind of entropy we use, et cetera, it's a good way to see where the model is uncertain about its output. In some LLMs, you get log probs. In some cases, you might not. So if the log probs are not present, we built a log prob generation module, which is also part of the secret sauce of Chainpool, where we generate log probs from the input and the output. And if you do get, that's great. We use the same source log probs, and we pass that into what we call a chain of thought module, which is the core algorithm, right? It does the chain of thought prompting to an LLM. It doesn't. Sometimes it does it to the source LLM. Sometimes it's very configurable. You can choose a different LLM. But the whole point is that you do this ensembling bit. You do the chain of thought, and then the ensembling bit you do it n times. N is a hyperparameter to the algorithm. It's kind of like number of judges. You have 5 experts in the room, and you see what they say, and you analyze results of the 5 judges. You get a result, and then you pass that into sort of a cleanup and normalization module, and finally we get a score between 0 and 1, saying how likely has the input-output pair hallucinated. Now we did a lot of benchmarking compared to other existing techniques at that time for hallucinations, self-check BERT, G-eval. A lot of them are published by very well-known research institutes. And we were able to beat them by a significant margin. And the reason was because we combined, the uniqueness was the combining of the chain of thought and the ensembling. So it was more accurate. It provided more understandable human feedback because there was an LLM in the mix. We give these beautiful explanations around why something is wrong. It was low latency because we, in the context of LLMs, I mean, we're working with different levels of latency here, but it was using batch inferencing. Like Chainpool by default uses batch inferencing, which is like essentially saying that all the arrows and boxes that you saw, all that happens in the scope of one single LLM call. That, of course, leads to much reduced cost compared to our adversary techniques. But that, Chainpool was great. We deployed Chainpool with a bunch of customers. It worked really well for hallucination detection till you hit the problem of productionizing these models and these LLM systems at scale, which is where cost comes into the mix. Chainpool makes one call, and I can give you one anecdote from one of our customers, which is a large education company. They're operating at about 100 queries a second, which is a reasonable scale. I mean, there's of course much bigger, but even at 100 queries a second, with a single extra LLM call, your eval costs can go up to in the millions of dollars. So it was a big challenge to come back to the drawing board and think about how we can solve hallucination at $0. Now, what we did was rather than of course we have to eliminate the LLM call. That's the biggest cash cow here. So we redefined the definition of hallucination, which was originally a much broader, areas where the models sort of, talking out of context or saying the wrong things. In context of RAG, hallucinations definition kind of just reduces to or boils down to, is the model talking within the context that it's provided, or is it adhering to the context? So because we were able to reduce the definition, hallucination detection essentially boils down to an entailment problem. And entailment, if you've done natural language before, there's entailment models called NLI models, which are very small BERT models. So we took those, and we've been able to train them efficiently. And we've actually, if I move here, we've been able to achieve better performance than Chainpool, which is LLM based. So it's really like, why use an anti-gravity pen when in certain cases pencils can work, and which is the whole point of our Luna effort. Luna is based on what we call evaluation foundation models, or EFMs. And they're much smaller models specifically designed to solve the hallucination problem. This is a chart of Luna's accuracy versus latency. So we are hovering, the general Luna accuracy hovers around 0.8, which is pretty state of the art in hallucination detection. But you can see that the latency, it's a local model. Like all the other methods are using LLMs. That's why you're dealing with like 3 seconds to 8 seconds latencies, which is in some cases just unfathomable. So we've been able to reduce it to sub-second with Luna. And same with cost, right? Like you're just running an off-the-shelf, like cheap GPU, and you can deploy these models on it. as opposed to using these LLM APIs to do detecting hallucinations. It really massively reduces your cost. These are some of our benchmark results that we published. You can see the accuracy numbers across. This is also still work in progress. We're still trying to improve them every day. But you can see Luna's performance across the different standard tasks compared to, say, some of these LLM-based techniques. And again, this is also on benchmark domains like customer support, financial reasoning. And these results also include some of the private data that we've evaluated our models on, that we get from our customers. So clearly you can see there's so much you can do with much smaller models. And I think the thing to remember is that hallucination essentially boils down to an entailment problem. So you can literally use a small-scale DeBerta model, which is doing entailment detection, which is a binary classification problem. So we've been able to do that and innovate on multiple fronts. Like we've done novel windowing, and we've done all kinds of very interesting training data curation to be able to come up with a high accuracy NLI model that can detect hallucinations across different tasks. We've also done efficiency improvements, like a single pass. It's a multi-headed deep learning model. So it's a single pass gives you 4 metrics, which addresses RAG quality in 4 different dimensions, hallucinations being one of them. The other RAG quality dimensions include how complete your output is. It may not have hallucinated, but it's not complete. How much of the chunks were utilized at the token level in the reasoning of the output, which chunks were attributed to. So these metrics together really help you evaluate and assess the quality of your RAG systems. And you can do that just with this one model. And this matters because of what I said. Like the whole low latency, low cost, high accuracy is the need of the hour, and it's pretty much uncompromisable. And as technical people, you sometimes think, oh, this is too big a problem to solve. But essentially, if you put your mind to it, you can essentially achieve. You can pretty much get there. Finally, I think we have the metrics that I spoke about. There's a whole host of other metrics that we offer as part of the Galileo platform, which are categorized into these categories. But since it's a platform, we allow you to add your own metrics. And you can see, because of all the Luna work we've done, there's a whole host of we call them $0 metrics, free metrics. You just deploy a simple model, and you get great evaluation metrics out of the box. That's it. I would love to connect. My name is Atin, so you can reach out to me on LinkedIn or atin@rungalileo.io. Yeah, thank you. Yeah, happy to take questions.
So how are you going to do all this observability once we put all these models and the queries in an enclave or encrypted queries? Have you looked into that?
That's interesting. We haven't come across this particular need, especially around enclaves, et cetera. But security has come up a lot. Like, especially maybe it's a little bit of an orthogonal issue that we've seen with customers, especially, for example, a lot of users are using Azure as OpenAI. Like very few people, surprisingly or not surprisingly, use OpenAI directly. Everyone goes through Azure. But then in Azure, there's a lot of confidential computing resources which are not employed yet in these LLM workflows. So that is work in progress. But that's always a need that people ask. Like, can you, I guess as Galileo, we hook into these systems. But the request usually for us is that if I employ a confidential CCV VM, or use this confidential computing infrastructure in my LLM system, would Galileo work or would it not? And for us, we are an algorithms company. Like, we focus a lot on deriving insights from the behavior of these neural nets. So it matters less where you run it. What matters for us is how fast we can run our metrics. I think that's where it kind of gets interesting, because right now our focus is to get low latency by running these metrics on certain kinds of GPUs. But the next phase could be that you essentially run it on a confidentially compute GPU. But that's not come up yet. Yeah. Awesome. If no other questions, yeah, thank you. I'm also available just to chat. Thanks.